Good afternoon, ladies and gentlemen. This is the long-awaited 2.6 families of functions video we've all heard about. I wanted to start off by talking about parent functions and their transformations. Transformations of a parent function is really just how we're shifting them around the graph. So let's first talk about definition-wise what a parent function is. All five of these are parent functions: linear, quadratic, absolute value. We're also going to have graphs that are going to be, what they call exponential. And then we're also going to have something that's called some kind of radical graph using radicals. But for all intents and purposes, we're just going to focus on these three right here. Again, this is linear, this is quadratic, and this is absolute value. And this is going to look like, in essence, really y equals mx plus b if you want to look at it like that. Quadratic, real simple, y equals x squared. And absolute value, real simple, y is going to equal the absolute value of x. And again, these are all the parent functions that all the other functions are derived from. So these are like the real basic, in other words, parent functions, and then all the parent functions have all these children functions of all these different kinds of translations and transformations. Our next slide here talks about some of the concept summaries of this. These are really good notes to have taken in your Cornell notes. Actually, the whole chart here. Let's first talk about reflections. Now, what reflections do, if you look at these graphs down here, is that just as the name sounds, it's going to reflect itself over something or through like a mirror. Take a look at the the black graph right here, and you can see the reflection of it in green right here. That's reflecting over the y-axis. And you can see the black graph again being reflected in the blue graph over the x-axis. And we're going to show you how to reflect over the y and how to reflect over the x-axis. As a matter of fact, let's go back up here and talk about that. The reflection over the x-axis, you're taking the opposite of the whole function. The reflection over the y-axis, you're just taking the opposite of the x value. So let's take a look at the one they had here reflecting over the y-axis. So they want to take this function and reflect it over the y-axis. So let's take a look. 3x plus 3, that's going to be this positive graph right here, because your slope is positive. Goes right through 3 as the y-intercept, just like this slope-intercept form says. And they want to reflect it over the x-axis. And if you take a look here, it's almost like this arrow reflected to this arrow reflected to this arrow, and as a matter of fact, this point is reflected with this point. Black was the original, and blue right here is going to be the translated function of the reflection on the y-axis. The way to do that is, if you recall, to take the opposite of your x value. That's how you're going to reflect it over the y-axis. So let's move on to some other transformations. Here they want to go ahead and reflect it over the x-axis. Well, if you recall, now you take the opposite of the entire function. And if you wanted to simplify that, it would look something like this. The next transformation are the stretches and compressions. A vertical stretch, or really just sometimes they call it stretch, is when you're going to have a multiplication factor that's greater than 1 towards your function. A compression is where you're going to be actually compressing it down towards the x-axis by a factor between 0 and 1. And this factor between 0 and 1 usually is in the form of a decimal value or perhaps a fraction. And again, those fractions or decimal values have to be between 0 and 1. Sometimes you will see it written like this, but your a value has to be in between 0 and 1. Here, for this stretch, where you're stretching it away from the x-axis, your a value is simply going to be greater than 1. Let's take a look at this in action. Here they've given us a function where they want to multiply it by 3. They want to transform it into a new function. So what they're going to do is multiply all the y values, remember f of x is y, by 3. Here is the original chart of f of x. And all they're doing is multiplying all your y values by 3. 3 times all these, 3 times 2, 3 times 2, 3 times negative 3, 3 times 1, 3 times negative 2. And it's going to spit out all these values right here. That's our transformation. So in essence, our t-chart for this new transformation is going to look like this. And then all the values multiplied by 3. Next one is a vertical translation. Oh, these are examples of the vertical translation. Sorry about that. First, we're going to have to think about what vertical means. Vertical means up and down, correct? And here they have a real basic function, y equals x, this blue graph, this black graph right here, and the translation of down 2. So what they've done is they've taken it right here and moved it down 2, taken it right here, moved it down 2. They've moved the entire line down 2 whole units. What did they do on the graph, or excuse me, on the table? They just took all these values right here and subtracted 2 from them in this column. Next problem, y equals x squared minus 1. Now if you recall, your parent function is going to be y equals x squared, and they're actually doing something to it. They're actually taking that whole function and going down 1 unit right here. So our first black graph right here is going to be the parabola. We originally had it at the origin. It was already moved down 1 unit. Now they want to move it up 5. So you start right where you're at, -1, and then go up 5 units to where you've got the new blue graph. These arrows right here represent the idea that each and every point on the black graph has moved up 5 units, just like this chart here says. All your y values add 4 to it, because you've already subtracted 1. Moving up 5 is just a plus 4. Let's take a look at these two functions right here. They asked us what is the connection between these two. Here, if I were to graph this, again, it would be a straight line with a slope of 2. This is the same line, but what have they done to it? They've had a vertical translation down 3 units. So you would say that this is shifted down 3 units. What about the graph y equals 3x up 2 units? Well, that should be relatively easy. Take the graph y equals 3x and then shift it up 2 units. What about a horizontal translation, where they're shifting all of the coordinates here? All of these coordinates are going to be moved over Excuse me, went too far on that one. All of those units are getting shifted over. I believe that is 2 whole hours. Let's take a look at the problem. The graph shows the projected altitude of a airplane scheduled to depart an airport at noon. If the plane leaves 2 hours late, what function represents this transformation? Well, again, they've taken the airplane altitude. All airplanes start on the ground, they go up, and all airplanes eventually end on the ground, hopefully not too hard, but that is your typical graph of the altitude of an airplane of a 2-hour flight. And they've just gone ahead and shifted it over to the right 2 whole units. Now you're thinking, wait a minute, this says x minus 2. Well, there you have it. This is the idea of your general format for this graph. Where the H and K are the horizontal and vertical shifts, and the A again is going to be your stretch or compression. So if you look at this, this is going to be x minus h. H is 2. Think about it again. H is 2, so you're going to actually move 2 to the right. The idea here behind the negative h is just do the opposite of what you think it is. It looks like negative 2. Wait a minute, it's h. Just do the opposite and go to the right. Let's talk about another reflection situation, real similar to that first graph. All we did was to flip this over the y-axis is to go ahead and take the opposite of your x values. And if you think about it, take a look at these two coordinates right here. This one here is negative 2, 3. And over here, we've taken the opposite of those values, so now it's positive 2, 3. You took the opposite of all the x values to create that blue line. How are these functions, how are the functions y equals x and y equals x minus 2 related? In other words, how are the graphs related? This here is going to be a shift up or down, or left or right. Well, this is going to be a shift down 2 units. Because you're subtracting 2 from the entire parent function. How about this horizontal translation? What is the graph of y equals x squared minus 1 translated up 5 units? Well, that's real similar to the one we saw in the earlier example. We're going to take y equals x squared, add 5 to negative 1, so it's simply going to be a plus 4. That would be your graph, or excuse me, your function representing this idea. Here's a summary of all those ideas that we've been working on. I strongly suggest you putting these in your Cornell notes, and we look forward to seeing you guys soon.